So hello, everybody. So before I delve into perhaps more details about what I do, let me describe the overarching goals behind my field of research, which is theoretical high-energy physics. So this field is concerned with basic, if you want, questions about our universe, like what is it made of? Like what are the simplest building blocks used to make all of matter or everything that's around us? For instance, if you consider water, you probably know that water is made of a multitude of identical molecules. Each of them consists of 3 atoms, and then if you zoom in on a particular atom, you would not see, but we accept that it consists of a nucleus made of protons and neutrons, and around this nucleus, you can imagine electrons orbiting around it, these small dots. And then if you zoom in even more into one of the components of the nucleus, here a neutron, you would decompose it into 3 smaller objects, which we call quarks. So the first question, is it the end? Can you go any smaller than the quarks? Is there something even more fundamental? Another question that comes immediately is how do all these elementary particles, do they interact with one another? How do they, what's the forces between them? So what's commonly accepted is that there are 4 forces that can describe all of physics. The most common familiar to all of us, is gravitation, obviously. Then there is electromagnetism, which would explain how the electron is moving around the nucleus in an atom. And these 2 forces are more obscure, perhaps. The weak interaction is responsible for radioactivity, among other things. And the strong interactions would explain, like the 3 quarks I had on the previous pictures, how they stick together. Why do they remain together to form always a neutron? Why is that stable? But the main purpose behind the theory part of the field is to write equations that can describe the universe. Like, can we define models, and then can we solve them and make predictions for real life? Okay, and for instance, regarding these 4 forces, 3 of them are described quite well, actually extremely well, by quantum physics, while the 4th one is described by another theory called general relativity. So immediately you would see that some questions arise, like, can we reconcile these 2 theories? Like we have quantum physics on one side, gravitation described by general relativity on the other, but can we describe them all together? And it is an important question because there are some phenomena, like black holes, where really both effects are as important as one another. So you need to have a coherent, consistent description for everything at once. You cannot just consider one and then the other separately. So one possible theory of quantum gravity, which would be a unification of all forces, is called string theory. So of course I'm not going to give any detail about it, but at least I can say that it changes the way we consider elementary constituents of matter. Now we do not say that quarks or electrons are the smallest thing you can find. We would say that actually the smallest thing you can find is a string. And depending on how the string is vibrating or undulating or wiggling, it would look to us like an electron, or it would look to us like a quark. So you see already it's a different paradigm. And then there's another important puzzle. It's a bit more technical, but it's also as important perhaps. You see, I told you these quarks, they always stay together. The neutron is very stable, and these 3 quarks, they never stray from one another. And it is a fact that you can never see a single quark wandering alone. So this is something we do not know how to explain. How is it that the strong force is so strong that they want to stick together? Theoretically, we have no explanation for it. And more generally, when interaction is too strong, physicists don't really know how to describe it adequately. So these puzzles are still very much unsolved, sorry. And one of the promising ways to tackle them is based on a conjecture, which I would like to describe using an analogy. So you should imagine these 2 ships. They look very different, right? This is a completely random spaceship. This is a cruise ship. And now I'm telling you, it's the first time you're seeing them, okay? And now I'm telling you they're actually equivalent in the sense that if you take this ship apart, somehow you can reassemble all the pieces and you would be able to build this. So you might be dubious, but then they start. So of course we don't know how to take them apart. It's much too complicated. But what we can do is look into a very specific detail, like we can isolate a single part of one ship, and then someone else, or perhaps the same person, will realize that he or she can find the same part on the other ship. And every time we do this, it matches. Like every time we identify, I don't know, a screw, a bolt, anything, we can find the exact same thing on the other side. So in physics, it's this equivalent is between two theories. One is the string theory, and the other is called the quantum theory. But the idea is the same. They look very different, but somehow there's this conjecture that they actually measure the same thing. Like everything you can measure on one side, well, there is something that will match on the other side. And this has been tested. First of all, yeah, it's called the holographic principle, if you want to hear the name. It's an example of what's called the holographic principle. So it has been tested extensively, like people have many tests, but there is no proof, there is no basic understanding of it, like rigorous way of building a bridge starting from one side and just arriving to the other, like in a step-by-step way. This is not explained. Right? So, and this is essentially my long-term research objective, to, at least on a simplified example, which I will describe perhaps, is to try to, on a simple example, understand how we can go from how I can take apart the cruise ship and how I can then put all the parts together to make the spaceship. Like, can I give you a recipe or a way to proceed? Okay, so because the only way to proceed is to consider a simplified example, and this is what I want now to describe. It's called an integrable example. So integrability is actually not specific to quantum physics, on which I'm working. It's something that appears across all fields of physics. And essentially, it means that you consider a system that is simple enough that you can solve it exactly. You don't need to make any approximations. You can just solve it, and you see the solution, and then you understand it, essentially. So of course, you can imagine that this is not common. It's actually most systems you won't be able to solve it. Like, if you want something realistic, you have too many parameters to take into account. You can just imagine, this simple example. If I just want to describe the trajectory of the basketball, bouncing off the floor, if the floor is flat, well, it's very simple. You can write two equations, which would predict where the basketball will be anytime in the future. Now, if you're bouncing the ball of corrugated steel, for instance, you can already imagine that it's much more random. It's not random, but it's much more chaotic. That's the word for it. And for instance, even if I'm throwing the ball in front of me, because of the shape of the floor, it could come back to me at some point, right? And in this sense, most physical systems will be like this. They are too difficult to solve, to predict. So in quantum physics, it has already been proven useful to consider simple systems. Even at the very beginning of quantum physics, people focused, for instance, at the hydrogen atom, which is a single proton, which is a nucleus, and then an electron, a single electron orbiting around it. And what they observed, first of all, observations showed that the electron cannot go in any way around the proton. Like, for instance, let's say it can move only on circles. The circles cannot be of any size. It could be either of this size, or this one, or some bigger sizes, but there could not be a trajectory in between. And classically, there is no classical explanation for it. This is what quantum physics explains, this quantization of the trajectories. And it's sort of the first success of quantum physics, because it's an integrable model, so we can solve it exactly, and we see that indeed the trajectories can only be some very specific circles, if you want. Of course, if you consider more perhaps interesting or more complicated atoms, like the oxygen, if you're interested in water, then suddenly you cannot solve it anymore because it's too complicated, but you can use the intuition you got from here, and you know that the same conclusion will essentially can be drawn. So now in my research, what I do is I consider a simplified universe. Instead of really taking into account that there should be all these particles, they should interact with all these forces, I remove most of them, remove most of the forces, and then I'm saying, okay, let me study this model. What can I understand from it, like more in a deeper way? So just to give you a picture of how simple it is, so if this is how I define the real world, this is my world. You see, so of course you don't understand the equations, but you can believe me if I tell you that this is much simpler than what you might have to do. So the question now, okay, now if I'm starting from this idealized situation, can I really solve it? Actually, you need to develop new mathematical techniques, but that's what I'm working on. Of course, I'm not alone. And because even though we know it's integrable, so it should be solvable, it's not easy to do. And finally, going back to the conjecture I was describing you, on this particular case, can we really, starting from whatever this theory is, construct step by step the string theory on the other side? And there is hope that this could be done, so that's why I'm doing. And with that, I'm done, and I thank you for your attention.
Thank you for a very interesting talk. I have a question regarding when you gave the example of an hydrogen atom, so it has one spherical orbital, so that's not a chaotic system. This is what you're saying.
Yeah, it's more like, so, of course you're right, I simplified. Not all the orbits are spherical, but I'm saying just you can compute all the orbits, essentially.
But you also have, let's say, oxygen. So we have s orbitals, you have 2, and you have p orbitals. You can still calculate the density or the probability of an electron to be in a certain orbital.
No, I think you cannot do it exactly. You have to make approximations. I don't know which ones, because it's not what I do, but I think, so, no, you cannot do it exactly in the sense that, yeah.
Okay, so this is my question. So you cannot do it exactly, you can approximate,
yeah.
But if you can do approximation, wouldn't it be less chaotic? I mean, because you're calling it
No,
chaotic.
you're right, yeah.
Okay.
Sorry, I interrupted.
Okay, no, it's okay, I understand. Thank you.
Yeah, it's exactly this. Yeah, if you made approximations, and yeah, exactly, you simplify a little bit the systems, and suddenly you can progress, yeah. That's true.
Thank you for this interesting talk. Back to your original question, can quantum theory and string theory be combined? Is there any proof right now out there, or
so
you're still a way far
yeah,
away from that?
so string theory is supposed to, yeah, indeed to be the solution. I mean, it's not a proof because, for instance, there is no way to test string theory. Like, it doesn't have yet predictions that we could test using experiments. So it's still a proposition, I mean, proposal. But right now it's the best one we have. So yeah, I cannot say more essentially. But yeah, essentially no, I mean, in the sense that people don't know how to combine yet gravitation and quantum physics. It's not completely known how to do it.
Thank you.
Thank you. Thank you very much. Thank you very much, Gwenaël.
Thank you.